Alright, so last time we were looking at implementation of a list ADT using an array. And I said the main bottleneck with array implementation is you need contiguous block of memory to store your list. So if you want to store a very large list of say 1 million integers or 1 million elements, it could be of any data type, then you need so that much amount of contiguous block of memory available. If not, then you will not be able to create that list. So that's the main weakness, especially if you want to work with all this big data thing. So an alternate solution is to use what is called a linked list. Um, Now, the idea behind a linked list is you store each data at different memory locations. So since you are storing at different memory locations, you do not need contiguous block of memory, but kind of as what do you call overhead is you want to store where consecutive elements are and what memory location elements are. So for example, if this is what you want to store, like 4 integers 20, 45, 12 and 17, with an array you can just create a contiguous block of memory of 4 bytes each, just 16 bytes, 4 elements, and you can store these 4 integers. Whereas in the case of a linked list, what you have to do is, so this is the data which is an integer that you want to store. So you package the data along with some pointers. So let us first see what is called a single linked list. So the data is stored along with what is called the next node pointer, and you all know what a pointer stores. Pointer stores address of where some other element is. So the next node pointer stores the address of the next data node. So that's called, so we have the terminology now called node. So the node stores the data as well as the next node pointer, and the next node pointer stores the address of the next data node. So now as you can see here, in addition to the data nodes that you have 20, 40 that stores the data 20, 45, 12 and 17, we also have here what is called a head node. So we'll see in the implementation we keep track of, because you can think about, do we need to store the locations of each of these nodes? No, really we don't need to really keep track of where each node is stored in memory from a coding point of view. So they are created somewhere and stored in memory. From a coding point of view, we need to keep track of only where the head node is, and from starting from the head node we can visit every data node, and that's what we are going to see. So we are going to see a store where the head node is stored. So we'll have what is called a head pointer that stores the address of the head node. Now the head node is a dummy node, it doesn't store any data. So the data portion of this node is just junk, or you don't need to fill up any data. Now the next node pointer of the head node stores the address of the first data node. So this is the next node pointer, and it stores an address, so it is 4 bytes in size. So any pointer that stores a memory address, we are going to assume in this course is 4 bytes in size. So it stores the address of the next data node. Now the head pointer stores the address of a head node. So again, remember, pointers always store address, memory addresses. So the head node is created starting from address 104, and that's the address that the head pointer is storing. So using the head pointer, we can access where the head node is. So now the next node pointer in the head node stores the address of the first data node, which is at address 120 in this example, and that's where the first data node is. And there we have our data. Using some member functions of the node class, we'll see all the implementation details soon. We can access what data is stored in that node. And then the next node pointer of that node stores the address of the next data node. So you have 136 here, and that's where the next data node is stored, which is the data is 45. And then This node stores the next node address, which is at 156, and you have the node there with the data 12, and the next node pointer address is 176. So it stores the address of the next data node, and that's also the last data node, because that's the last data element that you want to store in the list, which is 17. And then so there's no subsequent, there's no data node further down. The next node pointer stores 0, which is null. So 0 or null means it doesn't store any address. So you cannot access any address using this next node pointer value. So both these are the same. So this is how we have to visualize it as a node, and in memory that is how things are implemented. So again, as you came up with these numbers, it need not be like increasing memory addresses like this. It could be anywhere stored in memory. Wherever there's a space to store one data node, a node will be created there and stored, okay, dynamically whenever you want to create a node. So as you can see here in this figure, you are eliminating the need to have contiguous block of memory. But the overhead that you have to pay for that is you have to store where the address of the next data node. Okay, so you have to package whatever the data you want to store. It could be an integer, it could be an object, anything. You have to, along with that, store the address of the next data node. Okay. Any question on this so far? Single linked list. All right. Now we also have what is called a double linked list. Now if you look at the single linked list, and we'll see all the functions soon, but the key thing to be noted is we can visit the data nodes only in one direction. So if you want to say retrieve the third element in the list, and you can also see there's no explicit indexing, in the sense that we don't have a member variable called index and say this is index 0, index 1, index 2 and so on. There's no such explicit indexing of the data nodes. But still you should be able to retrieve what's the third element in the list and what's the data in that node. We should be able to do that, and we'll see the code for that. So you can see, you can if you want to like say retrieve the third element in the list, you cannot do like what we do in array. When you say array pointer of that index, you can right away get the address of that where that third element is stored, and you can retrieve that value right away without sequentially accessing the array, right? So we said we can do that in constant time, data of one time. If you remember that earlier thing that we saw. If you want to retrieve where an element is stored in an array, you can say a of 2. I know the base address where the array is starting, say in this example 200, and 200 plus 4 times 2, 4 because we're storing integers, we get 208, the address where that element is stored, and we can right away retrieve it. We don't have to sequentially go through index 0, 1, 2 and then retrieve that value. Whereas in a linked list, we don't have that facility of using the index explicitly. So what we have to do is we have to really start from the head node for any operation and then traverse through the linked list. So that is why, so we can also we can traverse only in one direction, in the sense that from the head node you can visit this first data node, from the first data node you can go to the second data node. So from the second data node you cannot go back to the first data node because it is only in one direction. So in order to get around this problem, we can have what is called a double linked list, in which you can traverse in both directions. But in order to be able to do that, you have to pay an additional overhead, in the sense that for each node, data node, will have what is called the next node pointer, similar to a single linked list, but we also will have what is called a previous node pointer that stores the address of the previous node. So the next node pointer stores the address of the next data node further down in the list, and the previous node pointer stores the address of the data node that is previous to this node. Okay, so let us look at this example here. So here I am starting, say my head node is stored starting from address 100, and the head node again is a dummy node, is not going to have data, And you can also see, does it need to store any value for the previous node pointer, because there's no node really previous to the head node. The head node is kind of really the starting node of that list, and it's not a data node. It's just like a kind of an auxiliary node. An auxiliary node means it's not a data node. It will store some useful information about the data that you're storing in the list, and basically it stores the address of the first data node. So that is stored in this next node pointer in the head node, and that is 116 in the example, and using that you can visit this first data node. And here we have the data, and we'll come to this previous node pointer quite soon, but let us traverse in the forward direction first. So from this node we can visit the next node at address 132, which is here, and the data 45, and then the next node is at 152, the next node is at 172. Now this is the last data node, so there's no data node following this, so we'll have the next node pointer as 0. So this is similar to what you saw in a single linked list case. Now to traverse in the reverse direction, we'll have, similar to the head node, node called the tail node. So the tail node, its purpose is to store the address of kind of what is called the last element in the list in the forward direction, and which can also be considered as the first data node in the reverse direction. Okay, so the tail node is stored somewhere at address 196, and that is kept track of using a pointer called the tail pointer. So the tail pointer stores the address of the tail node, similar to how the head pointer stores the address of the head node. The tail pointer stores the address of the tail node, and in this example it is 196. And the tail node is also a dummy node, so it doesn't store, it's not a data node, so we don't really need to have value for the data, and there's no node further down, so there's no need to have the next node pointer set up. But of course you have to have these allocated, because everything is like under the created using a node class, so these you have to allocate space for the data and next node pointer, even though you're not filling them up. Okay, so the previous node pointer of the tail node stores 172, which is the address of the node previous to it. Okay, in the sense that this is the last data node in the forward direction or the first data node in the reverse direction. So that's where this node is stored, and this data node stores the address of the previous data node, which in this case is 152, and using which you can access this node. And it stores the previous node address, which is 132, the previous node pointer, and then 116. So now you see, this is the last data node in the reverse direction. There is no node previous to this node. So you can say there's a head node, but the head node is not a data node. So the previous node pointer of the last data node in the reverse direction, which is also the first data node in the forward direction, there's no data node previous to it. So you store 0, null, similar to how you store null for the next node pointer for this last data node here in the forward direction. You store 0 for the previous node pointer for this data node in the reverse direction. Okay, so this is how we are going to implement a double linked list. So in this module we'll focus on single linked list, and in modules 3 and 4 we'll focus on double linked list. Okay. Any question on the idea behind single and double linked list? Okay, so let me save this video.